Ever wondered how we can trust AI to make life or death decisions? Like, how do we know a self-driving car's brain won't suddenly think a stop sign is a tree? The answer lies in something called DNN certification, a mathematical framework that proves AI systems behave reliably. But here's the catch. Doing this efficiently has been like solving a puzzle with missing pieces. Let's break it down. At the heart of the challenge is a fundamental mismatch. Neural networks are built from tiny units called neurons, and traditional certification tools operate at that neuron level, essentially writing rules for each individual cell in the brain. But when AI runs, it uses tensors, which are super-efficient data structures that process massive chunks of information at once. The problem? The math that works on paper doesn't always translate to real-world performance. It's like trying to follow a recipe written in French while cooking in a kitchen that only speaks Spanish. So how do we bridge this gap? Researchers developed a compiler, a smart translator that converts neuron-level rules into tensor-friendly code. But it's not just a simple translation. They created two key tools: a stack-based intermediate representation, IR, to track the math, and shape analysis to handle tricky parts like how data expands or contracts during calculations. Think of it as a bridge between the microscopic rules of neurons and the macroscopic power of tensors. Here's where it gets fascinating. When they tested this system, they discovered something unexpected. The way data is structured in these certifiers creates a unique kind of sparsity, like empty spaces in a puzzle. Existing tools weren't built for this, so they invented a new format called g-BSCR. It's like a special box that holds puzzle pieces more efficiently, making everything run faster. This format uses a tuple, DSBZ. The D is a default value for missing spots, and B are smart blocks that store only the important data, and Z tells you the full size. It's like a map that shows where the action is without the clutter. The results? For the first time, developers can create and test new certifiers without getting lost in complex code. And the performance? Almost as good as hand-optimized tools. This means we're one step closer to trusting AI not just because it's smart, but because we can prove it's reliable. So what does this mean for the future of AI? It's not just about making machines smarter, it's about making them transparent. And that's a game changer. Stay curious, and let's keep exploring the science behind the tech.